Hello guys, welcome to this new video. So this is going to be question 8, the last question in the May 2023 time zone 1 paper 2. So here we're given photons with this wavelength are incident on a metallic surface, and the maximum kinetic energy of the emitted electrons is 1.8 electron volts. And we need to calculate firstly the work function of the surface. So this phenomenon is known as the photoelectric effect. And so very briefly, what this is about is like we have some surface, some metal plate or something, and we have photons being emitted here. So these are photons, and the energy of a photon can be given by the formula h times f, where h is the Planck's constant and f is the frequency. This can also be rearranged a bit because we know that the speed of a wave is just lambda times the frequency, so the frequency is c over lambda. So if we plug this in to this formula, we will find that the energy can also be written as hc over lambda. And then a photon here hits an electron. Let's say there's an electron here in the metal surface and it hits this electron. Then some of this energy of the photon will have to be used up to remove the electron from the surface of the plate, and this is known as the work function. It's like the energy required to remove the electron or bring it to the surface, and with the remaining energy of the photon, the electron will be emitted with some kinetic energy, with the remaining kinetic energy. And so this is the basics of the photoelectric effect. And this also has a formula in the data booklet which just summarizes this process, where we say that E max, so the maximum kinetic energy of an emitted electron, is just the energy of the photon minus the work function. As the photon is incident with some energy, some of that energy is used up to remove the electron, the rest of it is given to the kinetic energy of the electron. And we're going to need to use this formula here. So we know the maximum kinetic energy of the emitted electrons, and we also know the wavelength, so we know the energy of the electron, so we can calculate how much energy was required to remove the electron from the metal surface. So we know, I'll just write this down again, so the energy is h times f minus the work function. So we can rearrange this for the work function. This will just be h times f minus the energy, but we know h times f is just hc over lambda. As here we were given the wavelength, so it's going to be a bit easier to calculate with this formula. So now we just need to plug in these values, making sure that everything is in the correct units. So we know that Planck's constant is 6.63 times 10 to the minus 34. We know the speed of light is 3 times 10 to the 8. And then we know that the wavelength was 468 times 10 to the minus 9 meters. But currently this expression here gives the energy of a photon in joules. And well, we need to calculate work function in electron volts, and the energy of the electrons are in electron volts. So we need to convert this energy of the photon from joules to electron volts. And the way we can do that is just by dividing by 1 electron volt, so 1.6 times 10 to the minus 19. So now this expression will give us the energy of the photon in electron volts. And if we subtract this, and if we subtract 1.8 from this, the kinetic energy of the electron, then we'll find that the work function was 0.86 electron volts. So this is how much work it took for a photon to remove an electron from the metal surface. And then we need to find the longest wavelength of a photon that will eject an electron from the surface. So here we are technically saying that we want to find the smallest energy of the photon that will just about remove an electron from the metal. We can assume then that the kinetic energy will be 0, as we just want to find the energy required to remove this electron. We don't care like how fast it will come out or anything. We just want to see the smallest energy photon that can do this. So if we use the same equation, we know that we want an electron with 0 kinetic energy, or very close to 0, a little bit more. And this will be equal to the energy of the photon minus the work function. And well, the work function we have already calculated, the metal remains the same, so it doesn't matter what's going on, the work function is just a constant for a specific metal. So again, we can rewrite this with the wavelength, and then rearrange for the wavelength. This is going to be hc divided by the work function. And now we just have to plug it in. So lambda will be 6.63 times 10 to the minus 34 times 3 times 10 to the 8 divided by, well, the work function was 0.86 electron volts, but now we need to convert this back into joules, as Planck's constant and everything has to be in joules. And when we work with this formula, usually it has to be in joules, except if we want to calculate it something in electron volts. So we do this by just multiplying this work function in electron volts by an electron volt, so that we convert it into joules, like this. And then we will find a wavelength of 1.45 times 10 to the minus 6 meters. So this is the longest wavelength that will just emit an electron. And then we are told that in an experiment, alpha particles of initial kinetic energy are directed at the stationary nuclei of lead, show that the distance of closest approach is about 4 times 10 to the minus 4. So let's try and think about what's going on here. So we have some lead nucleus, some Pb, and then we shoot alpha particles at it with some kinetic energy, known kinetic energy. And we want to find the distance of closest approach, which is technically the point where the speed becomes 0. And after this point, it will start getting repelled again. So we want to find this distance d when the speed is 0. So we can think about the energy conservation here. As at the start, we technically only have kinetic energy. If we are far enough, then the potential energy is approximately 0. And at the end, we have 0 kinetic energy as our speed is 0, and we have some potential energy. And due to energy conservation, we can say that the kinetic energy at the start will equal the potential energy at the end. And well, the potential energy can be found using the equation in the data booklet, K times big Q times small q over R. So this is just the potential energy of two charges close to each other and divided by the distance between them, and this is the distance we will have to find. So we can write that the initial kinetic energy is just this potential energy, as they are equal, like this. And then we can rearrange for R. So we want the distance. This will be just K times big Q, small q over E kinetic. And then we need to start plugging in. So the Coulomb constant is 8.99 times 10 to the 9. And then let's think about the charges. So we kind of have to know that an alpha particle has a charge of +2. So this is not really given here. It's also not in the data booklet. So we just kind of have to remember this fact. It can also come up in multiple choice questions, so it's worth remembering. So we have a charge of 2 electrons on an alpha particle. And well, we know we have 82 protons in a lead nucleus. So that means we must also have 82 electrons, as the charge of this Pb is neutral, so the number of electrons and the number of protons is the same. And then we need to divide by the kinetic energy, which is given to us in mega electron volts again, which we need to convert into joules again. So this will just be 5.9 times 10 to the 6. So this is how many electron volts we have, EV. And then we multiply this by another 1.6 times 10 to the minus 19, like this. And then this will be in joules. This will give us 3.99 times 10 to the minus 14 meters, which is indeed approximately 4 times 10 to the minus 14 meters. Yes. All right. And then the last question in this paper, we are told that the radius of this nucleus is 7.1 times 10 to the minus 15, and we need to suggest why there will be no deviations from the Rutherford scattering experiment. Well, first let's discuss why there could be a deviation, like why these deviations might occur. So if this is our lead nucleus, I just drew like a part of this, so like this circle would extend like this, but it's more zoomed in, that's why I only drew like part of this. And then we have this alpha particle here. And well, we calculated the stopping distance to be some distance like this. Some distance from the nucleus, it was 4 times 10 to the minus 14 meters. And we also know that the radius of this lead nucleus is 7.1 times 10 to the minus 15 meters. And well, this I drew wrong because this arrow wasn't measured from the surface, it was measured from the center. So the radius is always the distance when we plug into this formula, also with potential energy for electricity and for gravitation. This radius is always the distance between the centers of the two objects. So this was 4 times 10 to the minus 14 meters. So we see that this distance here is larger than the radius of the nucleus, so it's going to be somewhere further away from the nucleus pretty much. And well, in this Rutherford scattering experiment, these alpha nuclei were scattered because of the electromagnetic force. So like they're both positively charged, so there's going to be some electromagnetic force that is repelling this alpha particle. And if an alpha particle comes really close to the lead nucleus, like over here for example, then we will still have an electromagnetic force, but then we will also have the strong force. So if it comes really close, we also have a strong force. As a strong force is just a force within the nucleus that binds the protons and the neutrons together. It's technically what keeps the nucleus together, but this strong force has a very small range. So it's really only the size of the nucleus, it's very, very small. So if an alpha particle is this far away, it simply is not gonna have the range to go from the nucleus all the way to here. But if the alpha particle is really, really close, then it will have an effect, and that's when we will have a deviation. But since here, the distance of closest approach is quite far away, then the strong force will have no effect on the path, so there will be no deviation. And that's generally the explanation. So we can say distance of closest approach is larger than the nucleus radius of the nucleus, and so we will only have the electromagnetic force so the strong nuclear force, it only has a very small range, so it will not affect the path of alpha particle. Therefore, no deviation. As I said previously, we would only have a deviation when it comes really close, and the strong force also starts affecting the path over the electromagnetic force. And well, so this was the last question in the May 2023 Time Zone 1, Paper 2. I hope it was helpful, and see you in the next questions.